Welcome, ladies and gentlemen. This is a classic example of finding the area between two curves algebraically without the use of a calculator. Now, we can certainly check using our graphers, but this is the kind of thing we'd be expected to be able to do on a non-calculator portion. The numbers work out nicely, right? But we have some important concepts that we can practice in this problem from yesterday. All right, so let's go ahead and consider the region enclosed by y equals 4 minus x squared. We're thinking about that as a parabola whose orientation it looks like is upside down because we have a negative on my quadratic term, and a line, y equals 2 minus x. So let's get a nice picture and then see what region we're talking about. So I'll go ahead and consider a scale here. It looks like we're an upside down parabola, so maybe if we went 1, 2, 3, 1, 2, and if we did 1, 2, 3, 4, that might fit nicely. So if we went ahead and did our parabola in blue, I know its vertex would be given by 0, 4. And it looks to me like this parabola is going to have the same steepness as my parent function because the coefficient on my quadratic term is 1. So it looks like out 1, up and down 1 squared. So out 1, down 1. Out 1, down 1. Out 2, right, up or down 2 squared. So out from my vertex 2, down 4, out 2, down 4, and so it looks like here's our nice familiar upside down parabola. Now let's go ahead and consider our linear function. I'll do that in red. So for our linear function, if we think back to start value and then plus or minus rate of change times x, it looks like my start value, my initial value here, a y-intercept is 0, 2. And it appears as though we have a slope of a rate of change of -1. So as I move along this from left to right, down 1 over 1, down 1 over 1, down 1 over 1, and so on. Back, up 1, back, up 1. And so if I went ahead and considered the region bounded between these curves, it looks like we've got, looks like we're talking about a region right in here. The shaded region in here. And I told you about the night class that I enrolled in that you saw Cunning Baraboo. You can notice that I recently added to my schedule a shading class. So I'll be practicing with maybe some cross-thatch shading as well as some dashed and dotted shading. I'm still trying to perfect that, the light with the curved orange type thing, the dots to show that 3 dimensions. It's really difficult for me. In any case, luckily we're dealing with a 2-dimensional region here. So everybody, let's consider the area of this region now as a definite integral. How can we determine my points of intersection algebraically without the use of a calculator? No second calc intersect, right? Well, we can do that by considering the solution to a system. Graphically, the intersection of those two curves represents the solution to the system y equals 4 minus x squared and y equals 2 minus x. And so to find this point algebraically, we could simply solve the system where we set one curve, 4 minus x squared, equal to the other curve, 2 minus x, and solve for x. So if we want to find those intersection points exactly in algebraically, it would be the same as solving this system. So let's go ahead and add, subtract, multiply, or divide, get everything in one side in standard form. So I'll probably add over that x squared. It'll still remain a minus x. And then it looks like we've got 2 minus 4 equals -2. So let's see. If the dust settles and I've gotten in standard form, is that what we're getting algebraically? And now I can solve that quadratic equation, right? We have many methods. I'm going to go ahead and do it by factoring. It looks to me like this will factor nicely. So if I solve by factoring, I can utilize the zero product property. It looks like x and x, 1 and 2. And it looks like we need a -2 and a +1 in order to complete that factorization. So it appears as though I have points of intersection at x equals -1 and at x equals +2. So raise your hand if you had x equals -1 and x equals +2 for your points of intersection. Wonderful, you guys, that's great. So in order to get the y coordinates, we could evaluate this x. We could plug this x value back into either of my equations y equals because we know that those points must satisfy each equation because they're the intersection points. So 4 minus a -1 squared is 4 minus 1 is 3. I'll go ahead and label that -1, 3. And 2 minus a -1 is 2 plus 1 is 3. We already got that. 2 minus 2 is 0, so how about we'll label this as 2 comma 0. Okay, so we already got the x values. Now I want to know, raise your hand if you got these points as the points of intersection. Have we got all the way to the x and y? Now we've got, great, things hands down. Now we can choose. We can choose how best to integrate, right, in order to find the exact area of this region by hand and algebraically. Last class, we integrated, right, from left to right, and we integrated from bottom to top. The choice is yours, right? Ella was very efficient. She always wanted to make sure she could do it with one definite integral. And usually we can do that. And so does it make most sense to scan this problem, this region, from left to right and use little thin vertical rectangles? Or does it make more sense to go from bottom to top and use little thin horizontal rectangles? Well, I noticed if I were to draw a vertical rectangle that's typical of a rectangle in this situation, if I were to draw a little thin vertical rectangle, then regardless of where I draw that rectangle, as I move along the region from left to right, it's always bounded on top by that blue parabola. And it's always bounded on bottom by that red linear equation. And so if I choose to do a vertical rectangle and scan the region from left to right to fill up the space exactly, then I can do it in a single definite integral because we don't change boundary curves on top or bottom. You guys see that? No matter where I draw that vertical rectangle, it always touches the top blue. It always touches the bottom red, so I can do this in a single definite integral. So let's go ahead and do this with respect to x. If I'm going to set up a definite integral with respect to x, then I know I'm going to have x's in my integrand function. I know the values on my integral symbol, my limits, are going to be x values, right? So let's go ahead and say, what's the leftmost x value of my region? Right? What's the leftmost x value of my region? Jake? -1, thank you. Up until be ready. What's the rightmost x value of my region? Kobe? 2, thank you. My integrand, right? My integrand is going to be the height of my rectangle. Generalized. No matter where I draw this rectangle, this height is kept positive by always doing top curve solve for y minus bottom curve solve for y. That will ensure that, 1, I have x's in my integrand function, which is good news because I'm integrating with respect to x, and 2, perhaps more importantly, that I have a positive quantity. It doesn't matter where the x-axis is or isn't. It doesn't matter where this region is in relation to the origin. I can guarantee that the resulting area will be positive if I ensure that I have little positive delta x steps so that I'm scanning from left to right, right? Or bottom to top, and that I have positive heights of the rectangles by doing top minus bottom or right minus left. So let's go ahead and do top curve, solve for x. I'm sorry, solve for y so I have x's in it. We're going to scoop this down just a little bit. That's my blue integrand function, so that's going to be 4 minus x squared. And then minus my bottom curve. My bottom curve, solve for y, is 2 minus x. There is my f of x top curve minus g of x bottom curve from last class's activity. Raise your hand if you had this definite integral set up. So we had this definite integral set up. That's great. Now there ain't nothing to it but to do it. That is, we can evaluate this definite integral exactly and algebraically using indefinite integrals in accordance with the fundamental theorem of algebra. I will likely simplify this a little bit, and so I'm going to go ahead and rewrite my integrand here as 4 minus x squared minus 2 plus x. So I think this is going to be negative x squared plus x plus 2. If I were to rewrite that, did I do that correctly? Right. Negative x squared plus x, and 4 minus 2 is plus 2. And now we can evaluate this by hand by finding an antiderivative for my integrand function. So we'll go ahead and do negative 1/3 x cubed plus x squared over 2 plus 2x. We don't need the plus c if we're evaluating a definite integral, so long as we include, right, our limits here, negative 1 and 2. And our top limit all the way through. I get negative 1/3 times 2 cubed is negative 8/3 plus 4 halves plus 4 minus my lower limit all the way through. Negative 1/3 times negative 1 is plus 1/3 plus 1/2 minus 2. And any time is a good time for math fraction. So if we're dealing with this, I think we can finish this out pretty quickly. but I don't mind so much when we go to the calculator or when we don't. Because this is a non-calculator item, we'll go ahead and try to tough it out here. It looks to me like I'm getting 8/3 minus 1/3 is negative 9/3 or negative 3. I'm getting plus 2 plus 4 is plus 6. I'm getting minus a negative 1.5, so that's plus 1.5. So let's put it all together and see if we can't get 3 plus 4.5. I'm getting 4.5. We're getting that? Negative 3 plus 6 is 3. Plus 1.5 is 4.5. So I'm getting 4.5. Or 9/2. Raise your hand if you had 4.5 or 9/2. You already get that? No? Okay. So did we jump in too soon? Well, let's see. On my home screen, right? On my home screen, we'll go ahead and consider my original definite integral right at top, without any simplification, so I don't mess up with any negatives. And I'll go ahead and do Math 9 on my home screen to check this. Here we go. Lower limit, -1. Upper limit, 2. Expression 4 minus x squared minus parentheses 2 minus x close parentheses close integrand with respect to x. So depending upon your calculator, you may have, right, you may have just f in int for definite integral. Then you do expression, comma x, comma lower limit, comma upper limit, right paren, enter. In any case, we'll let it do its magic and voila, I'm getting 4.5 twice. That's good news. Okay. Today we're going to practice exactly this thing. We're going to calculate the area of irregularly shaped regions bounded between curves, regardless of where the x-axis is or isn't, regardless of where the origin is or isn't, so that we can evaluate these exactly. We will be doing some calculator aloud too. We're going to do some estimates as well using a trapezoidal rule and some numerical data, and then you're going to have some practice time at the end. At the last part of class, we will have to put the desk back, and so it's fine that you formed up with pairs. That's great, but at the end, we'll have to put them back to testing formation because of my advanced algebra class is taking a uniform test next hour. All right. So, what questions do you guys have on today's Bellwork? Then let's go ahead and take care of your OTL number 9 check. So our OTL number 9 did include graphs on the back of the half sheet from section 5.8. If you kindly staple that half sheet there, give yourself credit for those who completed at 23. There's a staple on the front table and a staple on the side table. Divide, enter, multiply by 2, and box in for the canvas score nice and big on top. You can write that on your half sheet or on your notebook paper. Just make sure I can see it, please. Make sure that your name, first and last, 2A, and number 9 are clearly labeled. Keep the stapler moving, please. And then go ahead and pass from the back to the front. Front row, if you make sure they're facing the same direction, or a little out of order, that's okay. I would ask that you make sure that they're facing the same direction with name on top, though. Thank you, guys. Thank you, Savannah. Everybody good? Thank you for your help, ladies and gentlemen. I appreciate that. Okay, so I want you to know that your rules quizzes are graded. I'm not sure about the time involved. You know exactly what was on your rules quiz, and so what I'm probably going to do is not pass back the hard copy today to make sure we have time for our discussion, but I will enter the scores in Infinite Campus during the second part of 4th hour so you can see exactly what you got. Once again, I am finished with your rules quizzes, okay? There's no surprise what's on that rules quiz or what's not on the rules quiz. I wanted to make sure that you could see your scores. So once again, I'm going to enter those in Infinite Canvas. You should check by the end of 4A today. They should be in Infinite Canvas so you can see exactly how you did. Okay, so your Moodle post this week involves the fundamental theory of calculus. Thank you for those of you who are already posted. You posted before I even saw you this week, and that's great. And I appreciate you making that part of your routine. Again, make sure that you're choosing an integrand function that has an antiderivative, and you'll evaluate that exactly, okay, using, right, one of those like natural log functions or exponential functions or trigonometric functions, and so your final answer should be exact for the person evaluating it, right? Don't change it to a decimal until you then check with your graphing calculator using tech tip and then verify that that decimal matches their exact answer and let them know, okay? So thanks for following the directions on the prompt. You guys are doing a great job with the discussion. I appreciate you following those directions. So last class we developed the definition of the area between curves. This is a big deal. A major application of integral calculus involves finding area of irregularly shaped region. We're still going to apply our same notion of a basic shape like a rectangle being used to fill up in its entirety an irregularly shaped region and get its exact area. And so the definition of area between two curves, if f and g are continuous functions and f is greater than or equal to g throughout the entire interval, kind of like a parabola, f was greater than or equal to my line in Bellwork, y equals 2 minus x, over the course of the interval g, then the area is given by the definite integral from a to b of top curve minus bottom curve. So our top curve was f of x minus our bottom curve. Our bottom curve is g of x. And then with respect to x. Ella, right, saw that in certain cases it was more efficient to integrate with respect to y. In that case, we wouldn't scan the region from left to right. Instead, we'd scan the region from bottom to top. Integrating with respect to y means that the limits on my integral symbol will be y values, right? No longer will I have top curve minus bottom curve with x's in them. I'll have right curve minus left curve to ensure that the now horizontally oriented rectangle heights are kept positive. So let's go ahead and take a look with the notation that I made up. So I'll call that y, solve for y sub t for the top equation, solve for y, and y sub b for the bottom equation, solve for y. We could go ahead and find the exact area of this irregular shaped region. Pardon the shading. My instructor gets fairly impatient, so I continue to take and perfect. Like, I feel like I miss it sometimes, and then every time I look at it, it's like I need to add a different one. Okay, so we'll go ahead and consider a scan with respect to x. That would be left to right. A typical rectangle then would connect the top boundary curve to the bottom boundary curve with a little thickness, delta x. As that delta x thickness shrinks to 0, I'm left with dx, the width of my rectangle. So then I just need the expression for the height of my rectangle. Well, my height of my rectangle is going to be kept positive by doing top curve solve for y. We'll call it y sub t, minus bottom curve solve for y. We'll call it y sub b. So my top curve with x's in it would be t of x. Minus my bottom curve, solve for y, would be b of x. And the limits on my integral symbol must be x values because we're integrating with respect to x. So my least most x value in this region, as I scan from left to right, would be the a or the c, or the b or the d. One would be a. So scanning from left to right, leftmost x value is a, up until rightmost x value of the region would be b. And there's our expression for the area. It's a definite interval. Sometimes we can do that exactly. Sometimes we have to use our calculator. If we're able to integrate with respect to x, right, in a single definite integral, then typically we do that because we're comfortable thinking in terms of x values and scanning from left to right, like we read a sentence or read a book. However, sometimes it makes more sense to scan from bottom to top. And so while this region can be done both ways, it'll give us a chance to practice a different orientation. Let's suppose now that we were doing this Ella's method and we're scanning from bottom to top. And so again, we'll still have an irregular shaped region. But now, to keep our rectangles height positive, we're going to scan from least y value to greatest y value to ensure my little widths of my rectangle, delta y, are positive steps here. So we'll go ahead and scan from least y value. In this case, the least y value is c, up until the greatest y value in my region. That's bounded by y equals d. And now we're going to go ahead and do horizontally oriented rectangles. That is, regardless of where I draw this horizontally oriented rectangle, it's bounded on the right by that line, it's bounded on the left by the curve, and so we can keep this quantity positive by doing right curve solve for x to ensure it has y's in it, minus left curve solve for x to ensure that it has y's in it. So let's go ahead and take my x sub r, right, is solve for x, that would be r of y. Oh, I'm sorry, every time. Minus my left-hand curve, right, solve for x would be L of y. And that will ensure that the quantity is kept positive. So again, if we're scanning with respect to y, we're going y values on my integral symbol, we're scanning the region from bottom to top. We're keeping our rectangle heights positive of our horizontally oriented rectangles by doing right curve solve for x minus left curve solve for x. And I have them solve for x for a couple reasons. One, so that I can have y values in my functions, integrated with respect to y, and have an antiderivative function with y's in it, right? And then the other one is I'm keeping that positive to ensure my little steps up from the bottom y value to the top y value, right, are kept as positive steps. All right, let's go ahead and think back to then our activity. Today, we're not going to do the algebraic evaluation of each of these. We're going to focus in on the conceptual setup. So once again, if we went ahead and labeled, right, these curves we saw from our activity last class, that the top curve here, y equals 2 sine of x, is shown in blue. The bottom curve here, the bottom curve, y equals sine 2x, we'll go ahead and show that in green. And so, if we consider this region, no matter where we draw this vertically oriented rectangle, we see that the top of that rectangle touches the blue curve, 2 sine x. The bottom of that rectangle touches the green curve, sine of 2x. And that's true no matter where oh boy. I just want this one. I just want this one right now. And no matter where we draw that rectangle, right, that's the case, so we can do this in a single definite interval. So let's go ahead and just set up. We'll scan from leftmost x value to rightmost x value in my region. And if I'm not mistaken, they gave us the limits. Didn't they say pi over 2 up until pi? So they gave us the limits there. Great. So let's go ahead and set up my definite integral, and we're not going to evaluate all the way. We'll scan from leftmost x value, that was x equals pi over 2, to rightmost x value, bless you, that was pi. Top curve in blue, top curve was 2 sine of x. Minus bottom curve in green was sine of 2x. That integrand function in parentheses represents the height of a rectangle, and it's ensured to be kept positive by doing top curve minus bottom curve. This dx comes from the width. So delta x thin widths that are shrinking towards 0, the result is a dx, so this represents the width then of each rectangle, and together their product gives me the area. If I sum up all those individual areas, we're left with the exact area of that areola shaped region. Now what we're going to do is, ready, magic, ... Right? We can go ahead and evaluate that either exactly and algebraically using the fundamental theorem calculus, or Math 9 on our calculator. And again, today I just wanted to make sure we're good with the concept. We'll have plenty of time next class practicing with our evaluation. Okay, let's go ahead and consider this region. The first method was to integrate this with respect to x. And so once again, I wanted to make sure that we're comfortable conceptually, and that's why we're returning to this. So again, if we were to consider the area of this region, I've got this blue curve. if x is equal to y squared, then when solving for y, so that we can integrate with respect to x, we produce positive root x. I'll go ahead and squiggle in that blue to match my top half of that sideways oriented parabola. And then we've got our green, y equals negative root x. And for simplicity's sake, we've gone ahead and broken that up in our picture so we can see exactly that depending upon where I draw my rectangle, right? Depending upon where I draw my rectangle, I'm going to have a different top and bottom boundary. So if I draw in this first region here, it looks like the bottom of my rectangle touches the green square root function, negative root x. But if I draw my rectangle over here to the right of this intersection point, then the bottom of my rectangle touches the red linear equation, much like the Bellwork. So what are we to do? Well, we can't evaluate this in a single definite integral the way we could in our Bellwork. We have to break it up. So how do we break it up? Well, we find our point of intersection, just like we did in Bellwork. It's just that now we need to figure out where those two curves intersect. How do we do that? Easy cheesy. We've solved a system of equations. And we can see with our color coding that that's the intersection of the green equation and the red equation. So to find that point of intersection exactly and algebraically, we'll simply set the green equation solved for y, that is root x, equal to the red equation solved for y, and that is negative 2 plus x. We had a blast from the past in trying to solve this radical equation. You guys had to remember, how do I solve an equation involving radicals? So my typical strategy is to isolate the side with the radical on it, and then square both sides to remove the radical. And then solve, right, using our regular means. So it looks to me like we could add or subtract to get everything on one side in standard form. It looks like we get positive x squared. This is just a single x. How's that? Is that better? Minus 4x minus 1x minus 5x plus 4. And now we can solve by factoring. And that opens up the zero product property, so it looks like x minus 1, x minus 4. Did I do that correctly? So it appears as though this function intersects, right? Intersects the other at x equals 1 and x equals 4. However, we can see that, right, x equals 4 in terms of the green will be extraneous. However, in terms of the blue, it would produce that other x coordinate up on top, x equals 4. And we can see through inspection that that's the case as well. 4 equals 2 squared, right? And so we've got this. And 4 also equals, right, 4 also equals 2. So we've got our points now, 4 comma 2, and negative 1 comma negative 1. So where do you get that? Negative 1 comma negative 1?
1 comma negative
1 comma negative 1. Good. I'm having a hard time plugging in a negative to that green square root function. So 1 comma negative 1. Much better. Are we right now? 1 negative 1 and 4 comma 2? Okay. Ladies and gentlemen, let's go ahead and set up our definite integral then. So if we're in the first part, up until this breakpoint, right? We'll go ahead and do our first definite integral. That will be the integral from 0 up until 1. Top curve is root x minus bottom curve is minus a negative root x. All with respect to x, plus the second part. Now we're going to go ahead and integrate from 1 up until 4 to get that second portion of the region. From 1 until 4, top curve will be given by root x, minus bottom curve will be given by y equals negative 2 plus x with respect to x. The sum of those two irregularly shaped regions' areas will then be the area of the entire region. And so now the favorite part, ready? Dot, dot, dot. Again, focusing on the setup. What questions do you guys have about the second one? Jake?
Why wouldn't we just go from Y again?
That's a great question. I would want you to ask Jake's question. Why don't we just integrate this with respect to Y? And that's what Ella noticed, right? She said, gosh, that worked out okay, but wouldn't it be much more efficient if, after finding my points of intersection, I recognize that a horizontally oriented rectangle, right, wouldn't change boundary curves, no matter where we draw this rectangle, right, isn't it bounded on the right by the line in red? X equals 2 minus y. And no matter where we draw that horizontally oriented rectangle, oh boy, that's rough. And no matter where we draw that horizontally oriented rectangle, it doesn't always touch the left parabola. So Ella's method is much more efficient. We still need our points of intersection, but now we're not going from 0 to 1, and again from 1 to 4. Now we're going to use these points of intersections for their y values. 1 comma negative 1 and 4 comma 2. And again, Jake will just do the setup. But yes, I would want you to say, hey, wouldn't this be better to integrate with respect to y? Nikki? Yes, thank you. Absolutely, thank you. So we're going to be now integrating with respect to y, and we need our curves then solved for x. Well, the blue parabola is already solved for x. That's great news. Well, we need to solve this linear equation for x. So x equals 2 plus y. Thank you. We need to add over that y. Math is hard for Mr. Fritz. Let's go ahead and get the region now by setting up a definite integral. So once again, this is just to practice our setup. We're now scanning from bottommost y value to greatest y value. So what's our bottommost y value of the region? Jake?
0.
The bottommost y value?
Oh. Negative 1. Then.
Negative 1. Good. Thank you. To the greatest y value in my region, Paige?
2.
2. Good. We're integrating with respect to y, so we need our curves to be solved for x so that I have y's in them. My rightmost boundary curve, right? My rightmost boundary curve minus leftmost boundary curve. That's going to ensure that the height of my horizontally oriented rectangle is positive. So here we go. Right curve solved for x is 2 plus y. That's in red. Minus left curve to solve for x. That's x equals y squared. So we've got right curve now minus left curve. That represents the height of my rectangle. It's just turned on its side. The dy still represents the width of my rectangle, infinitely thin. It's just now a vertical, right? A vertical little step, delta y, as we step up from bottom to top. Ready? Can we do it? Can we do the dot, 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 Annika? There we go. Dot, dot, dot. So we could do it Ella's way as well. If I'm not mistaken, that's going to be very similar to our Bellwork questions answer, too, right? In fact, we just have y's now. Great. Okay. So then the activity closed out with making sure we have a connection between, right, our with respect to x versus with respect to y, right? With respect to x versus with respect to y. What I want you to do right now with your partner is do it 2 different ways. Once with respect to x and once with respect to y. In this case, it doesn't matter which method you use. You can still do it with a single definite integral. The point of doing it twice is so that you're comfortable using, right, with respect to x, and make sure you have the correct kind of values for your limits and the correct integrand function, and with respect to y for the same reason. The correct limits on your integral based on which variable you're integrating with respect to, the correct integrand, and then the correct answer should be the same in each case. So everybody, let's go ahead and do these 2 with your partner now, once with respect to x and once with respect to y, to make sure that you're comfortable with either method. Again, both of these should give you the same answer. I'm going to go ahead and circulate. You'll have to find your points of intersection. Please catch my eye if you have a question. It's okay to talk about this with your partner, that's fine. You're finding the area of just the shaded region that's provided. Okay, so finding the area of just that shaded region that's provided. You can go ahead and solve. In just a minute, I'm going to start sharing. I'm going to start asking you to share some of your setup here, okay? Okay, ladies and gentlemen, let's go ahead and share your setup, please. For the first one with respect to x, we've got our red vertically oriented rectangles. So if we're integrating with respect to x, recall we're scanning from left to right. What would your limits be for the shaded region as we scan from left to right? Go ahead and tell the class when I call on you. Shannon? 0 to 3. Raise your hand if you have the same limits for with respect to x. That's absolutely right. Top curve minus bottom curve ensures the height of that red rectangle is kept positive. My curves need to be solved for y, so y equals, well, 9 is my top curve, minus the bottom curve, right? Solve for y is y equals x squared. So 9 minus x squared should be my integral function, right? And raise your hand if you had that already. Integral from 0 to 3 of 9 minus x squared with respect to x. Excellent, you guys, that's great. Let's go ahead and do the same setup for the same region, but now horizontally oriented rectangles, just to practice. Now when integrating with respect to y, my limits should be y values. Go ahead and tell the class my y value limits now as we scan the region from bottom to top. Sophia?
9 and 0.
So which is what? 0 up until? Absolutely, thank you. Those are y values and we're scanning from bottom to top, right? Bottom to top. Now to ensure that rectangle height that's horizontally oriented is kept positive, we do right curve minus left curve. And we need to have those solved for x. And so in this case, right, my right curve in red is half of the parabola y equals x squared. If I solve that for x, I get positive and negative square root of y. Which one of these will I be using? Brandon?
Positive square root of y?
Absolutely. We see that we're in the first quadrant where we have positive x values and positive y values, so we must use the positive root of y. in this case. So right curve is cos of root y minus my left curve solved for x. This is a function, right? I'm sorry, it's not a function. This is a relation. It is a curve. It is x equals 0, right? It's a vertical line whose equation is given by an x equals in the same way that the horizontal line had an equation. It was given by a y equals equation. So this is a boundary curve. It just so happens that it's on the y-axis also, but the boundary curve is x equals 0. So my left curve solved for x is x equals 0. That's my left boundary curve. That's my L of y. Awesome. In either case, we can finish these out through integration. We did that in our activity. Okay, so we've got 9x minus 1/3 x cubed. I think we can do it pretty quickly here. By finding an antiderivative function, evaluating my upper limit, evaluating my lower limit, subtracting the two. I'm getting 18. Raise your hand if you guys got 18. You guys getting 18? Great. What should we get when we do it with respect to y? Well, we should get 18 as well. It's the same region. We're just practicing the conceptual setup of a bottom to top scan and integrating with respect to y. Let's go ahead and verify that quickly. So here we go. An antiderivative function for my integrand would be power rule, y to the 1/2 currently would be integrated to y to the 3/2. Y to the 3/2 divided by the new exponent is the same as multiplying by 2/3. Evaluated from lower to upper. Go gadget arm, and so it looks like we get 9 in for y to the 3/2. It's interpreted as the square root of 9 is 3, then cubed is 27. 27 times 2 is 54, and then 54 divided by 3, it looks like I'm getting 18 again. So either way, whether integrating with respect to x or with respect to y, we still produce 18. That's pretty neat. Okay. Let's go ahead and take a look at an application of definite integrals now. Again, we'll apply them still in the realm of area, but instead of having, a symbolic equation, right? A symbolic equation that we can easily find an antiderivative to and evaluate in accordance with the fundamental theorem of calculus, let's go ahead and pretend that we're now given numerical data, that is tabular data, right, in a table. Let's go ahead and use this data and see if we can get an approximation for the area of this oil spill numerically. And so we don't have a function right now, right? We don't have a function. We can't find an antiderivative when you evaluate it at my upper limit, evaluate at my lower limit, and subtract the two in accordance with the fundamental theorem of calculus. Nor can we math 9 it for this first one. We're going to go ahead and consider this tabular data. So let's suppose that the distance east of the oil rig in miles after the 2010 Gulf of Mexico oil spill is shown in the top, right, the top row here, and it's paired with vertical distance between the upper and lower boundary of the slip. And so what we're talking about here is data that's measured, right, in miles from here, this oil rig. So east of oil rig, and then now we're doing the vertical distance that separates the top and lower boundary of the oil slip, measured in miles. How could we use this data to come up with an approximation for the area, right, that slip covers? Well, we could think about breaking that up into shapes. And so what I've done is I've gone ahead and broken that up into my distance east, right? Let that be my delta x in each of these shapes. And what shape seems to work best for this? Yeah, we're going to do a trapezoidal approximation here. A trapezoidal approximation. So I've gone ahead and drawn in my trapezoids. You go ahead and do the same every 5 miles, it looks like. This isn't always going to be a set delta x. We could still use the trapezoidal approximation even if we had data that didn't go by 5s every time. What if it went by 5 and then by 7 and then by 3 and then by 4, right? That's been showing up on the AP test as well. Irregularly delta x's, right? Irregularly spaced delta x's. We can still do a trapezoid shape. After breaking up your region into our 5-mile increments, keeping in mind that it won't always be 5, it could have been right different. It could have been 3 and 7 and 5 and 4. we need an expression that will give then the area of each of those trapezoids. So remember, our area for a trapezoid is 1/2 the sum of the bases times the height. In this case, we've turned these on their side. So my delta x, if it's equal, I can pull out front. If it's not equal, I have to do a single trapezoidal area calculation for every trapezoid. Because this is going by 5s every time, I can go ahead and use my trapezoidal approximation. It looks like 1, 2, 3. How many do we have? 1, 2, 3, 4, 5. Is that 6? So we'd be doing a t sub 6, yes? And we know that we can get our trapezoidal approximation by considering delta x over 2. And we can have our first function value, call it f of x sub 0, plus twice our second function value, right? Plus so we've got 2 times each of our middle function values, and then 1 of our last function value, right? Because that's only used 1 time in our thing. So let's go ahead and generate our expression. Here we go. We've got t sub 6 given by delta x, the width of each trapezoid, right? Well, the height of each trapezoid, but they're turned on their side. And so that would be how many miles? That would be 5 over 2 from the 1/2 of my formula times quantity. And here we go. Our first function value is the first height, separating the top and bottom of my oil slick boundary. So what's that? 3.5. Plus, we need 2 of this next one because it not only acts as the right side of my first trapezoid, it also acts as the left side of my second trapezoid. So we count its value twice. So we need 2 times 7 plus 2 times 11 plus 2 times 13 plus 2 times 13 plus 2 times 10 plus and can I scrunch it anymore? I can scrunch it more. Can you guys scrunch it more? You can. So I'm all about the home screen now, right? How did I do? Did I mess up at all with my notation? Is that what you guys are getting? Awesome. Let's go ahead and get our approximation and finish it out then. So it looks to me like we can do 5. I can do a single entry. And in my entry, I'm going to have 3.5 plus 2 times 7 plus 2 times 11. Let me know when I mess up. Plus 2 times 13 plus 2 times 13 again. Nikki, are you watching this? And plus 2 times 10. Plus my last 3. Dying to see what we get here. So we get it all. So 286.25 about. Raise your hand if you got the same thing. 286.25. And what would a label be on this? Go ahead and tell your partner. What would an appropriate label for this be? Well, let's consider our delta x values. Our delta x values were given in miles, right? And our distance separating the top of the slick and the lower boundary of the slick was given in miles. So miles times miles is square miles. Absolutely. So square miles is the way to go. We'll go ahead and box this bad boy because we want PDFable. All right. And what questions do you have about our trapezoidal approximation? All right. Now let's go ahead and add another layer to this. So let's suppose now that we had an approximation for, right, this upper boundary curve. And so let's suppose that the upper boundary is approximated by the function u of x. Then it looks like a quadratic equation there. I've got an x times an x, and then the negative upside down. So it looks to me like if we did u of x in blue, that's about this, right? That's about this. And if we do, oh gosh, this looks like a 1, 2, 3. What kind of function is L of x? A cubic, and so that looks like a cubic function. What if I did that in red? So that's something like this. And again, this is an approximation, so you can see how my slick, right, has squiggles and so on and so forth. These nice, smooth, well-behaved polynomials are just being used to approximate those boundaries. Now let's go ahead and get an approximation for the area enclosed by those curves, and this would be a calculator allowed question. So what are we going to do? Well, let's go ahead and enter my function for u of x and y sub 1 in my graphing calculator. My function for the lower boundary curve, y sub 2, right, L of x in my graphing calculator, and let's determine an appropriate window. We can then solve for my points of intersection just like we did in Bellwork, but now we'll have to solve for them using our grapher, right, using our grapher, and then set up a definite integral, and we'll be able to math 9 on our home screen. So everybody, here we go. First curve, u of x, will be negative 0.05. X plus 2, everybody enter it, please. Closed quantity, x minus 34. Flag. L of x is the cubic, 0.001. X minus 4 quantity. X minus 24 quantity squared. Bless you. And then plus 2.304. Take a minute and make sure you have those entered correctly, please. As we consider the window, I'm going to look back at our original tabular data. And as I look at our original tabular data, that can give me an idea of what might be an appropriate window. It looks to me like my x values, the distance east of O rig range from 0 to 30. So for my window, I'm thinking maybe I want to go negative 10 to 40 so that I'm getting a good picture. So I'm going to go negative 10 to 40. This may be good, it might not. For my y values, the distance separating the top and bottom is ranging from 3 to 13, but recall this is rising here above the x-axis, and so I'm going to have to account for that as well in my window. So I'm thinking that it might be helpful to go, oh, let's try negative 25 to 50. Now, if we don't like this window, if we don't like that window, we'll just change it. I don't know if this is going to be good or not. Here comes the top boundary curve. Looks like my vertical axis is a little tall, so I think I'm going to scrunch it down. Just get a nicer picture. Cool, I'm going to go ahead and change my window. I want to focus more on this region, so I'm going to compress my vertical scale. Instead of going negative 25 to 50, I'm going to go negative 10 to 30. Much nicer. Go ahead and find the window that you like, and we'll go ahead and set up a definite integral to evaluate. All right, so we're starting at 0, right? We're starting at 0. For on your, does it say we should start at 0, or we're going to the points of intersection?
It says the initial is, all it says is that the initial is vertical.
Okay, so we'll go ahead and start at x equals 0 then. So we won't need to find this point of intersection on the left, but we will need to find this point of intersection on the right, because the initial part is vertical, right? So the initial part is vertical. So we're going to go ahead and calculate that point of intersection. So let's go ahead and grab this. And let's go ahead and do a calculation. Second, calculate intersect. So that's second calc 5. First curve, enter. Second curve, enter. And we'll have to toggle using our right or left arrow keys to get closer to one intersection point versus the other so that it returns the one we're looking for. So it looks to me like we've got our intersection point here is given by about 31.665 492 ... comma 3.9296179 ... Mr. Fritz, why are you keeping all those decimal places when the College Board only requires that we keep 3? Well, I'm keeping all those decimal places so that I don't propagate my rounding errors too early into my final answer. I'm going to keep my decimal places and then only round to the third decimal place for my final answer. Is this my final answer? No. Is this my final answer? No. So I'm not going to round until I get to that last part. Then I'll round to my 3 places. So I'll go ahead and keep those. And now let's set up our definite integral. So I know that the exact area from 0, right, up until the point of intersection will be given by the integral from 0 up until what? Which one? Which value here? Yeah, the 31 one. Good. The 31.665492 of top curve minus bottom curve. Now, because we've already defined u of x and L of x, you can, right, it's okay on the free response portion of the AP exam, if you have a defined u of x and L of x, to do, get ready, do u of x right here in your integrator to save you time. You don't have to write it all down or lose points copying incorrectly with your decimals. If it's already defined in the problem, you can write that as u of x, its name, minus L of x, its name, and you must include dx or dy anytime you have an integral sum. So you have to include your dx. Now that we've gone ahead and set up my definite integral and showed that calculus, we can go to our calculator and math 9 it. Again, we've already entered our y1 as u of x and our L of x and y sub 2, so check it. On your home screen, you can call out the function named y1 and y2 and not have to worry about typing errors and getting the decimals wrong. So everybody, we can math 9, and we can integrate from 0 up until 31.6659492. And our integrand function, I want to do as u of x minus L of x. Well, I've already stored u of x in y1. So I'm going to go ahead and do vars, y vars, function, y1. That was my top boundary curve, minus bars, y bars, function, y2. And there's u of x minus L of x. And I have to type it all over again with respect to x. And now we're ready to go. It looks like my approximation with the trapezoid rule, right, is fairly similar to the approximation using those given boundary curves. So it looks to me like we're doing A-okay. So what are we going to do now? We're going to do approximately, and now is where we do our 3, guys. So we're going to do approximately 294.601 square miles. Awesome. What kinds of questions do you have about our oil slick application? Evie? Certainly. You do the expression first. So you do an expression first, then comma with respect to x, then comma lower limit, comma upper limit, enter. So expression, comma with respect to x, comma lower limit, comma upper limit, right paren, enter. Fussy. What other questions you guys have about our oil rig application? Then, ladies and gentlemen, this is where we are. So we've got OTL 9B was added as extra practice, right? So that we can make sure we've solidified these important skills before moving on towards the application of volume. So area between curves practice, that's out of 8. Please listen carefully. I would like for you to use your calculator. A lot of you use your calculator, like to find the points of intersection for numbers 1 and 2. Every other question you should do non-calculator first. And so number 3 would be an example on the AP exam of strictly non-calculator. Numbers 4 through 8 would be non-calculator eligible items. I want you to do non-calculator first, and then you can check with the calculator for numbers 4 through 8. So once again, calculator allowed would be 1 and 2. All the other ones you should be able to do non-calculator first. Then indefinite intervals worksheet to practice our antiderivatives algebraically and symbolically. That's out of 28, numbers 15 through 42 out of 28 for a total of 36. you're going to have an opportunity now to work with a partner and check with the answer key. So I just uploaded these to Moodle. You can check with your smartphone or electronic device as you're working together now. You can check those keys on Moodle. And you may work with another person. Keep in mind that at the end of class, we're going to have to scooch the desks back together. Okay, so we will have to scooch the desks back together at the end for my testing. What questions do you have about what the rest of the class period is going to look like? Okay, let's get started, and I'll save the recording and upload it to our Moodle site.